Welcome back. This is the fifth and final video in the series of enzymes and metabolism. If you like these videos and you'd like to subscribe, my gecko will be at the end of this video, and I'll put the entire playlist up here so you can come back and have a look at the other 4 videos if there's something you want to have a second look at. In the previous video, we considered a metabolic pathway, something like this, where a substance, we'll call it A, is a substrate, which gets converted into B, which gets converted into C, D, F, all with different enzymes along the way. And what we recognize is the big advantage of doing this, instead of just having a reaction where A gets converted directly into F, the big advantage here is that by having small sequential steps, any large energy shifts, energy changes are eliminated. There's no big heat changes, there's no big product changes. The molecules are changed sequentially and a little bit at a time, and that makes it a lot easier for cells to maintain homeostasis. Well, the business of homeostasis suggests something else too, is that cells, organisms have to be able to not only control reactions like this, but they have to be able to start them, slow them down, speed them up, stop them. They have to be able to regulate these processes. It's not like the requirements in a cell are constant all the time. They're always changing, and we have to have a way that we can create more reaction or less reaction. It's sort of like, well, it's much like cruise control a vehicle. If you set the cruise control at 60 kilometers an hour and you're starting to go uphill, the car will accelerate for you because it's maintaining that level. You need more gas to maintain that speed. Or if your cruise control is set at 60 and you're going down a hill, you actually wind up consuming less gas because you're just coasting, and it's not like there's no constant requirement for the same amount of fuel. Take that into our human body, yeah, it's the same sort of thing. Our breathing rate can be sped up and slowed down depending on what your needs are. So, for example, if you just ran around the block, you have an elevated breathing rate because your body's used up oxygen. You've got to get more oxygen more quickly so that you can maintain a normal balance, maintain your homeostasis. There's another example of the pH of blood. I mean, pH of blood, we've said it before, is about 7.35. Well, when you're doing things, when you're engaged in physical activity, that generates metabolic acids, and the pH of blood would have a tendency to go down. And you don't need your pH of your blood to go down. Like 7.2 is probably lethal, or 7.15 would be lethal. So your kidneys control the pH of your blood. And your body has ways of regulating all of these kinds of things. In a metabolic pathway, when you take it down to the chemical level, it's not exactly the same. In this case, let me just, if this was a complete metabolic pathway where this was the original substrate and this is the final product here, what would normally be the case is that the presence of this product would in fact inhibit that enzyme. And we talked about inhibitors already, that they would occupy the active site, or they'll occupy allosterically another spot on the enzyme surface. So if you need to regulate this thing, or this reaction needs to be regulated, as this concentration of this F, this product F, builds up, it will slow down the reaction. And why am I so bold as to say it'll slow down enzyme 1? Well, there's no point in slowing down enzyme 2, or 3, or 4, 3, or 2, because that would allow this to build up, which it doesn't need to build up. You don't need to stockpile these intermediates. It always goes back to, and here's the way it's phrased, this negative feedback, as it's called. That's negative feedback, or feedback inhibition. Feedback inhibition is where a product inhibits the first enzyme in the pathway that's dedicated to the production of that product. Let me give you another example here. Let's suppose that we had a metabolic pathway that was A, B, C, D, F, G, something like that, where this intermediate here could, depending on the cell's needs, could be converted into either of two different substances. Well, what happens if we don't need any more G? You're going to put E's on here. E1, E2, E3, E4, E5. Can you see which enzyme product G would inhibit? The answer is E4, because that's the first enzyme which is dedicated to the production of G. It's not going to be this one, because that would cause this to shut down. And of course, if G were to inhibit enzyme 4, you can see that this reaction, this set of reactions in here, isn't going to happen, so it means that C is even more available to be used to convert into the final product over there, which is D. So that's examples of negative feedback, or in this case it's feedback inhibition, where a product, the presence of a product, shuts down a set of reactions which is dedicated to its production. Very important concept. I think that's it for this set of videos. Like I say, if you enjoy them, don't forget to subscribe. If you missed something, you want to go back and have a second look at it, here's the playlist for this whole video set up here. Thanks very much.